When you have two particles that exert forces on each other, they create an action-reaction pair. When we want to define a system where we're looking at the behavior of one or the other or both of these particles, there's a couple ways that we can do that. One of them is to define each particle as its own system. In that case, each particle is moving on its own, and the force from the other particle counts as an external force acting on our object. So in that case, we can consider a system about particle A, and the force from the force of particle B that's acting on part A will be an external force. This force will change the kinetic energy of our system because we have the external force doing work on particle A that will change the kinetic energy. Another way we can define the system, though, is to not look at particle A as one system and particle B as a separate system, but rather to treat particles A and B within the system. In that situation, the interaction between A and B is also inside the system. In that case, the external work is zero because the action-reaction pair, the forces between A and B, are all within the system. They're not external forces anymore. What we're going to do then is to define this interaction and the work done by this interaction not as an external work that changes the kinetic energy, but rather as a potential energy, which we define as we label as a capital U. When the internal forces of the system do work, that's when we have changes to the potential energy of the system. Basically, you're storing that energy in this interaction, and as these internal forces do work, they release some of the energy as work is done on them, or as these interacting forces do negative work, that energy is stored in the potential energy. We said that potential energy is what is affected when you have internal forces that are doing work on the system. That's what we have in this situation where we have two particles that are interacting with each other and nothing else. So these two particles have internal forces due to their internal interactions, internal to the system that includes both particles, and they interact with nothing else, meaning there's no external forces acting in the system. In this case, if these forces of interaction do negative work, that results in a positive increase in the potential energy of the system. That's shown by the negative sign. If the work done is negative, that means that these interaction forces are taking kinetic energy away from the system, and that energy shows up as potential energy. Furthermore, the total work done by the internal energies can also be considered as the work done by particle A and the work done on particle B, since both of them are part of the system. If the work done is negative, that means that energy is taken away from kinetic energy and put into this potential energy. Think of it as being stored as this potential energy, or vice versa. If the potential energy decreases, then the kinetic energy would increase as a response to that. The potential energy would release stored energy. That energy would go into kinetic energy to make one particle or the other go faster. Thus, the potential energy interaction, is storing energy inside the system. And we're calling it potential energy because it's energy that is not observed directly in the system at a given moment, but has the potential to be released or to be converted into kinetic energy specifically at a later time. One situation where this shows up is in gravitational potential energy. When we think of an object that is acting under gravity, that object is on Earth, and that object feels gravity pulling it downwards. In this situation, the object is our system. Gravity is an external force acting on the system. And that's one way to consider the motion, that we have an external force that will change the kinetic energy of the system as our system, the object, accelerates downward because of gravity. However, what we can do instead is, instead of treating just the object, just the ball, as our system, we can actually treat the ball and the earth as the entire system. The reason why we do that is that not only is there a gravitational force on the ball, a gravitational force of the earth acting on the ball, we know that from Newton's third law, there's also a force of the ball acting on the earth. There's an equal opposite reaction of the ball pulling the earth upward. And so instead of treating the ball itself as a system, we're going to treat the ball and the earth together as a system. So our system is the ball and the earth, and this includes the gravitational interaction between the two objects in our system, namely the ball and the earth. In that case, we don't have an external force. There's not an external force of gravity. There's an internal force of gravity. And so we can define the potential energy in the system as the work done by gravity on the ball, the work done by gravity on the earth, and the negation of that amount. As we're doing work, we're taking that energy out of the kinetic energy, storing it as potential energy. We're including the earth in our calculation of the total work done. We're saying the total gravitational potential energy is the work done by gravity on the earth and the work done by gravity on the ball. However, even though there's an equal and opposite reaction, there's force of gravity on the ball, force of gravity on the earth is so massive that we typically imagine that the earth doesn't move. And in that case, if there's no displacement, we can neglect the work done by gravity on the earth, since we imagine the earth to be a stationary basis and that the ball is moving relative to a stationary earth. We know that on a cosmic scale that's not the case, but on the scale of a small ball moving up and down a few meters, that is a useful approximation. In this case, if we want to know the change in potential energy, then the change in potential energy is the work done by gravity on the ball. If the ball, the ball would feel a downward force of gravity, and we're assuming that the ball is going up by an amount delta y, in that case, there is negative work being done on the ball as it goes upward. There's negative work done because its displacement is positive, the force on it is negative, and so there'd be a net negative work being done on it. Since this work of gravity would be taking away kinetic energy, it would be slowing the ball down, we imagine that energy is not disappearing, that energy is going into gravitational potential energy. And in this case, we can finally distinguish. We've been talking about a change in gravitational energy, which is equal to the force times the distance, essentially, since gravity is a constant force. But we can also break this up. We can say that this is the final gravitational energy minus the initial gravitational energy, and we can say that delta y, the change in y, is a final height, a final value of y, and an initial value of y. In that case, instead of treating it necessarily as a change in potential energy and a change in height, we can define gravitational potential as mgy. In that situation, we can treat the gravitational potential energy of the ball as a fixed value at whatever height it happens to be in. And when we look at its change in height, we see the change in gravitational energy, gravitational potential energy, and we'll be able to predict the change in kinetic energy as a result of that.